Today we are going to discuss about torsion. So what is torsion? When a body is subjected to twisting. See, the example for torsion is when turning a screw by using the screwdriver. So we apply torsion. We apply the torsion. A shaft is there, one end is holded, and it is subjected to rotation, twisting. So that is torsion. So during torsion, the shear stress will be developed in the material, the shaft. In the first unit, when it is subjected to axial load, the stress may be tensile or compressive. Tensile or compressive. And when a body is subjected to bending, the nature of stress may be tensile or compressive. Tensile or compressive. One surface it will be tensile, another surface it will be compressive. But now another stress they are going to study, that is shear stress. In case of bending also, some amount of shear stress will be developed. That will be very, very less. That is not that much important, not influential. So we will not give much importance to that. But the shear stress produced due to torsion must be given importance. Must be given importance. Body is subjected to twisting moment, there will be a shear stress. So the another example for this is a generator. Here is a turbine. Here is a turbine. When the turbine is rotating, when the turbine rotating, the turbine may be a gas turbine, hydraulic turbine, or any one of the turbine, any one of the turbine. So what turbine do when power is given input, that is maybe hydraulic power or whatever it may be, if some power is given, that will be converted into rotary motion. That will be converted into rotary motion. So the generator will be rotating. So these two are coupled. These two are connected. When the turbine is rotating, the generator also will rotate. So during rotation, the power is generated. Power is generated. So here, when the power is applied, the shaft will be subjected to twisting. The shaft will be subjected to twisting. When the power is applied, it will be subjected to twisting. The type of stress developed is shear stress. Shear stress. See, the shear stress is a that is developed in the shaft, but due to torque, the torque is what is torque? It is in unit is Newton meter. That is, the tangential force is acting on the shaft. The tangential force is acting on the shaft. When it is subjected to tangential force in the radius will become torque. Will become torque. Now the shaft. This is a shaft. It is subjected to a torque. The cross section is like this. Cross section is like this. So here torque means a tangential force is acting. Tangential force is acting around the shaft. Tangential force is acting. So this is center point. So now this is radius. This is force. So what is torque? Torque is equal to force into radius. Force into radius. So the force is converted into torque. So this is torsion. When it is subject to torsion, it will be the shaft will be twisted. The shaft will be twisted. So that is what here it is shown. While a shaft is subjected to twisting, what is happening? What is happening? See, this is a shaft without applying the torque. Before applying the torque, it is like this. You can see the groove are cut in the surface along the length. It is all are parallel, all are straight and all are parallel, and also it is parallel to the axis. Parallel to the axis. When it is subjected to twisting moment, when it is subjected to twisting moment, how it is twisted? No, you can see how it is twisted. You can see here also. Here square shaft is given. These are all circular shaft. How it is twisted, it is shown in figure. So this is happening. This is happening in the shaft. So now our objective is to find the stress. We know that the stress developed is shear stress. It is subjected to shearing. The stress developed is shear stress, right? Now we hit some assumptions as we did in the bending. Here also almost the similar type of assumptions. Initially, we are assuming that the material is homogeneous. The material is homogeneous. So the property of the material is constant in all point of the material. So we are assuming material property is constant at all point of the material, that is homogeneous. So another one is it is elastic. It is elastic. We are not dealing with the plastic stage, we are dealing with only elastic stage. So within the elastic limit, it Hooke's law, stress is directly proportional to strain. Here shear stress is directly proportional to strain. Here stress is directly proportional to strain. And elastic limit of proportionality, it is within the happening within the elastic limit of proportionality, already we have seen. And finally the cross section remain plane after application of twisting moment also. Twisting moment also. For example, you consider this shaft. Here we have considered a plane. We have considered plane. This is before applying the load. Even after applying the load, the plane remain plane. The plane remain plane. So that is what we assumed, right? Now you take a shaft like this. You take a shaft like this. So now we are going to derive the derivation, right? Here we have a shaft. This is a shaft. The shaft length is L. The shaft length is L, and radius is capital R. You can see in the, this is a side view. You can see from in the side view the radius of the shaft is capital R. Capital R. Now it is subjected to a twisting moment T. It is subjected to a twisting moment of T. Length is L and radius is R. Radius is R. Now we are interested to calculate the distance B dash. B dash. We want to calculate the arc length B dash. Now initially the point is at B. Initially the point is at B. When it is torque is applied, it is moved to B dash. It is moved to B dash. B to B dash. It is twisted. It is twisted. Now we are along the length. It is twisted. We are taking this angle is phi. This angle is phi. This angle is phi. See, we are taking this angle as phi. And also in the side view you can see this angle. This with respect to the center of the axis of rotation. This is about this, it is phi. About this, it is theta. About this, it is theta. Now you can find the value b dash by two ways. By two ways, you can write b dash equal to b dash is equal to length into phi. You can put length multiplied by phi. You can put, otherwise radius multiplied by theta. Both are same. Both are same. This distance is, this is theta. Theta multiplied by radius also this value will give, and phi multiplied by the length also will give this value. This value. Now what is phi? Phi is a strain. Phi is a strain. The shear strain. Phi is, we have calculated shear strain. Phi is equal to r theta by L. So this is a value. Already we have discussed, we have studied shear strain. Shear strain. What is shear strain? Or we can say Young's modulus, modulus of rigidity. What is modulus of rigidity? Shear stress divided by shear strain. Shear stress divided by shear strain. Then phi is equal to tau by G. What is G? Modulus of rigidity. Tau is shear stress. If you compare these two, if you compare these two, you will get tau by G is equal to r theta by L. You can write this as tau by R is equal to G theta by L. G theta by L. So this is one relation. This is one relation. Tau by R is equal to G theta by L. This is one relation. Now here we are taking capital R. Capital R. So capital R, at capital R, shear stress is equal to tau. See, this is a side view. This is capital R. Capital R. At maximum radius, the shear stress is equal to tau. shear stress is equal to tau. If you want to calculate proportionally, if you want to calculate at some place, small r, at any radius r, if you want to calculate, we can calculate like this. Tau, let us take at this point shear stress is equal to tau r. Tau r. So then tau by capital R is equal to tau r divided by small r. Tau r divided by, this is radius. The shear stress at radius capital R is this. I am taking some small r. At small r it is tau r. Tau r. So we can say, right, tau r is equal to tau by r multiplied by r. Capital R, this. Okay. Now we are going. The next step is, what we are going to do is, we are going to calculate resistive torque developed in the material we are planning to calculate. Now, how to calculate the resistive torque? Say this is the cross section of the shaft. Now I am calculating, I am taking a small elemental area. I am calculating a small elemental area. The area is dA. Area is dA. What is the radius at this point? It is r. Radius is r. So now I am interested to calculate d torque at for the small elemental area. That's what I am putting dt, small elemental area. So how to calculate torque? Torque into force into distance. Force into distance. What is force? Force is equal to stress into area. Stress into area. Now at this radius, let us assume that the stress is shear stress is equal to tau r. Here also we have taken the same thing. At any radius r, it is tau r, but capital R it is tau. Capital R it is tau. So at any radius r, shear stress is tau r, area is dA. Then the torque transmitted is force into what? Force into radius. Force into radius. What is force? Force is equal to stress into area. So tau r into dA. What is this? This is force multiplied by radius. Multiplied by radius. Now, what is tau r? Already we have calculated tau r. You can replace tau r by this. So now tau capital R multiplied by small r dA into r. So this is equal to tau r into r square into dA. This is dt. We want to calculate for entire area. We want to calculate for entire area. So integrate it. Integrate it. Well, if you integrate it, integrating. So then torque is equal to tau by r inside. This is r square into dA. R square into dA. Do you know what is r square into dA? Already we have studied integral a into y square dA. Y square into dA. Y square into dA. What is this? This is I. This is I. Similarly, integral r square into dA is equal to j. This is called polar moment of inertia. Polar moment of inertia. Polar moment of inertia. J is equal to, for circular shaft, it is pi d power 4 by 32. Pi d power 4 by 32. So now this is J. Then what is the equation? T by J is equal to tau by R. Tau by R. So this is second relation. This is second relation. Now you compare the second relation and first relation. Here also we have tau by R. Here also we have tau by R. Then the torsion equation is T by J is equal to tau by R is equal to G theta by L. G theta by L. So this is the torsion equation. This is the torsion equation. What is T? T is applied torque. Torque applied. What is J? J is equal to polar moment of inertia. What is tau? Tau is equal to shear stress. And what is R? R is equal to radius of the shaft. Actually here you have to put capital R, that is outermost radius. Outermost radius. He will get outermost radius. Then G is equal to modulus of rigidity. What is theta? Angular twist. Angle of twist. What is L? L is equal to length of the shaft. Length of the shaft. So this is the torsion equation. Now you can see the torsion equation. The derivations are given. So this is a torsion equation. This is a torsion equation. T by J is equal to G theta by L is equal to tau by R. Tau by R. Here tau is equal to shear stress. R is equal to what? Radius, that is d by 2. L is equal to length of the shaft. Length of the shaft. G is equal to modulus of rigidity of the material. Theta, this is angular twist. Angular twist. T is equal to torque applied. Torque applied. J is equal to polar moment of inertia. Polar moment of inertia. So how to calculate polar moment of inertia? Let us see. You will see how to calculate polar moment of inertia. J is equal to integral A, sorry, R square into dA. R square into dA. You take a circular shaft. Circular shaft at any radius R. Now I am taking a elemental ring. I am taking a elemental ring. I am taking a elemental ring. Right? The for the link, the radius is equal to how much? Radius is equal to R. What is the thickness of the elemental ring? It is dr. It is dr. Okay. Now you substitute in this equation. You substitute in this equation. The equation is let us take capital. The outer radius is equal to capital R. Outer radius is equal to capital R. At any radius R, I am taking elemental ring, and the thickness of the elemental ring is dr. Thickness of the elemental ring is dr. Now, if you substitute in this equation, integral R square. What is dA? How to calculate dA? dA is equal to 2 pi R, 2 pi R multiplied by dr. Am I right? 2 pi r is a circumference multiplied with thickness. Multiplied with thickness will give the area. So now this is 2 pi we can take outside. Integral r cube into dr. The what is the limit? It is 0 to capital R. 0 to capital R. Now 2 pi into what is the integration of r cube? It is r power 4 by 4. 0 to capital R. Now 2 pi r power 4. R power 4. If you substitute R, we can substitute d by 2. Or you can substitute R is equal to d by 2. Also you can substitute, no problem. You can substitute. Generally, we take in diameter pi d power 4 by 32. Actually, it's supposed to come. Let us take d by 2 because from here to here, it is d by 2. So d by 2 over 4 divided by 4. Already if we substitute 0, it will be 0. Then what is the equation? 2 pi divided by 4 multiplied by r power 4. 2 power 4, how much it is? So 4, 8, 16. It is 16. So if you cancel this, it will be 2. This is d. So d by 2. D by 2. So now the equation is pi d power 4 by 32. Pi d power 4 by 32. So this is polar moment of inertia. Polar moment of inertia. Equation is this. General equation is this. For solid shaft, polar moment of inertia J is equal to pi d power 4 by 32. Pi d power 4 by 32. For hollow shaft, it is pi d power 4 minus small d power 4 by 32. So outer diameter is capital D. Small diameter is inner diameter is small d. So pi d power 4 minus small d power 5 32. Similarly, for a thin shaft, that is just like a ring. Just like a ring. A radius with thickness of t. Then 2 pi r cube into t. So these things you can calculate. Now we are going to solve one problem. We are going to solve one problem. Objective is to calculate the diameter, determine the size of the shaft. Determine the size of the shaft. Initially, uh, what should be the diameter of the shaft? What should be the diameter of the shaft? Diameter of the shaft. If this shaft is to be replaced by hollow one, this is if it is replaced by hollow one, and internal diameter is zero point 0.6 times outer diameter, determine the size. And so now, if it is a solid shaft, first we find the diameter. If it is hollow shaft, find the diameter, and how much amount of material is saved, you got to find. So first let us calculate the diameter of the shaft. What is the equation? T by J is equal to tau by R. Let us not consider the third portion. You consider only these two portions because this two is sufficient. Now first step is to calculate the torque. So what is power equation? What is the equation for power? Power is equal to 2 pi nt by 60. So this is a power equation. Here you have to find the value of torque. You have to find the value of torque. Then what is torque? Power multiplied by 60 divided by 2 pi nt, 2 pi n. So that is a torque. So now what is the power? Power is equal to 250 kilowatt. You substitute in watt. So 250 multiplied by 1000 multiplied by 60 divided by 2 pi n. What is 100? It is 100. So calculate the value of torque. Calculate the value of torque. What the value is? 23885. 23885. 23885 Newton meter. Newton meter. The unit is Newton meter. Right? Torque we calculated. What is the value of J? Tau is given in the problem. What is the value of tau? Tau is equal to 75 Newton per millimeter square. It is given 75 Newton per millimeter square. Now you substitute in this equation. In this equation, you substitute all the values. What is T? T is equal to 23,885 multiplied by 1000. Why 1000? It is in Newton meter. It is in Newton meter. So convert the Newton meter into millimeter. Right? So divided by J. What is J? J is equal to pi by 32 d power 4. D power 4. Let us check d power 4. That is equal to shear stress is equal to 75. It is in Newton per millimeter square. 75 divided by R. R is equal to d by 2. You can put d by 2. So in this equation, only unknown is diameter. Only unknown is diameter. You can calculate the value of diameter. You can calculate the value of diameter. This is by assuming solid shaft. Solid shaft. Now, if you take hollow shaft, then what will be the equation? What will be the equation? Here it is given that internal diameter is 0.6 times outer diameter. 0.6 times outer diameter. Then equation you apply the hollow shaft dimensions. So T, the same value 23885 into 10 power 3 1000. This is torque divided by J value. For hollow shaft, what is the J value? It is pi d1 power 4 minus d2 power 4. What is d1? What is d2? d1 is outer diameter, d2 is inner diameter, divided by 32. That is equal to 75 shear stress divided by d1 by 2. d1 by 2. We are interested in the maximum stress. Maximum stress will occur at the outer diameter. Outer diameter is d1. Outer diameter is capital as a d1. So now from this equation, you can find the value of d1 and d2. d1 and d2 you can calculate, right? Because we know d2 in terms of d1. You have to substitute d2 is equal to 0.6 times d1. Already it is given. Then you can calculate the value of d2 and d1. So now finally you have to find material saving. How to find material saving? So you have to find the volume of material. If you want to find if it is solid shaft, what is the volume of material? If it is a hollow shaft, what is the volume of material? You have to find. So what is volume? Area into length. Area into length. What is the cross section area? If it is a solid shaft, that is pi by 4 d square. This is cross section area multiplied by L. This will be the what? Area volume of solid shaft minus pi by 4 d1 square minus d2 square. What is this? Area of the hollow shaft multiplied by L divided by volume of the solid shaft pi by 4 d square into L, pi by 4 d square into L, right? So now you can calculate pi by 4. This pi by 4 you can calculate. This L, L, L you can calculate. Then the equation will be d square minus d1 square minus d2 square divided by d square. If you know the value of d, d1, d2, you can find the value of into 100. You put into multiplied by 100. That will give percentage. You put 100, it will give percentage. Now let us see the values. So these are all the values. Diameter is equal to, if it is a solid shaft, diameter is equal to 117.5 millimeters. 117.5 millimeters. And if it is a hollow, outer diameter will be 123. That is D1. D1 is equal to 123 millimeter. Inner diameter is equal to 73.8 millimeter. And the percentage of saving in material is 30 percentage. 30 percentage. 30 percentage. So these are all the results. These are all the results. If it is solid shaft, this is a value. If it is a hollow shaft, this is a value. If it is the saving in material is 30 percentage. So we want to transmit some power. We want to transmit some power. If you use solid shaft, we need to use more material. If you use hollow shaft, we can save 30% of the material. 30% of the material. The similar thing we have discussed in the bending also. In case of bending, instead of, if you keep the beam like this, it will give one bending moment. This will keep like this one bending moment. So if you both are same cross section area, but this can take more load. We can take more load. For same load, here the stress will be less. Similarly, this is a solid. If you take a hollow beam like this, for same cross section area, this will take more load. This will take more load. So for same cross section area, by changing the shape, we can get more load carrying capacity. More load carrying capacity. The same thing we have seen in torsion also. In torsion also, there we have to select a material such that it has more moment of inertia. In case of bending, we have to take a material shape such that it will give more moment of inertia. But in case of torsion, you have to select a material, select a shape which will give more J. As J increases, stress will decrease. So load carrying capacity will increase. What is the equation? T by J is equal to tau by R. If you want to calculate the stress, tau is equal to T by J multiplied by radius. So as J value increases, tau value decreases. Tau value decreases. And load carrying capacity will increase.